我做不来，我非常不爱它那个 converter。因为从我那个是硬把那个 converter 算那个正出来的，就没有那么 insightful about 这个 converter 算。我看了看他的，就是哇，像扣的值，反正我确实不会，我确实没想到扣。
我今天开始看。
之前不是很爽过吗？
2天，我周末2天出来改作业。
Professor, would you post lecture note 9 to the record?
Yeah, I will try to post it as soon as possible.
Oh, okay.
Today I'm going to finish this lecture 9 and then I will try to post it. Hello everyone, welcome back. Last time we talked about Chambolle-Pock, which is an algorithm for solving set point problem. Chambolle-Pock is also known as PDHG, which is prime-dual hybrid gradient method. The method can be, so one iteration of the method can be described as the following. So we try to search for 3 iterates, xk and yk and x bar k. So the algorithm looks like this, and now let me show you how can we view Chambolle-Pock as an instance of the inexact proximal point in general, the one which we solve for 0 in a set. Once we show it is an instance, we can automatically obtain the convergence of Chambolle-Pock method. In this theorem, we are going to show one iterative Chambolle-Pock method looks like this, satisfies the framework, which is for IPP framework. And once we have this condition, the two norm of the matrix K squared times tau 1 less than or equal to sigma, then we are gonna also have the inequality for the IPP framework, which is this one. So given this pair xk, yk, we need to find these two pair of points, xk plus 1, yk plus 1, and the ones with tilde. And also two scalars, lambda k plus 1 and epsilon k plus 1. So these two are the inclusion we need to check based on the three updates here. And we also need to check this inequality.
You can just lambda k plus 1 is 1 if you divide by.
Yeah, we are going to take lambda k plus 1 to be 1 and epsilon k plus 1 to be 0. So for notation, we are going to use the superscript to denote the iterate from the real method, the CP method. And for the subscript, this denotes the IPP framework. For example, here, these iterates means the ones for the IPP framework. And these iterates are from the CP methods. So we take lambda k plus 1 and we take lambda k plus 1 to be 1 and epsilon k plus 1 to be 0. The four iterates are as follows. Xk plus 1 and x tilde k plus 1 from the IPP framework are the same as the xk plus 1 from the CP method. And for y tilde k plus 1, it's the same as the yk plus 1 from CP. And so for these 3 points, we just take something that already exists in the method. But for yk plus 1, this is different. It's yk plus 1 from the CP method with this difference between x bar and x. So checking this inclusion is straightforward because this is the same as the first one here. Right? Because we take lambda k plus 1 to be 1, and if you divide the whole thing by tau 1, they are identical. And also using the definition of xk plus 1, x tilde k plus 1 in IPP framework. So let's check the second one. So let's check the left-hand side of the second inclusion. Let's plug in the definition for yk and yk plus 1 in the IPP framework, which is this one. Right, so the first line, just plug in the definition for YK plus 1 and YK in the IPP framework. We are using this line here, right? This is just this part is just YK plus 1 in IPP framework. Here is just YK in IPP framework. And the rest we just copy from here. This line, just copy from here. Right, and then we factor out how to rearrange the terms. We get the second line. And from second to the third, we use the definition of x bar k plus 1 in the CP framework. So the many terms will cancel out. This one with 2xk plus 1. We cancel 2xk plus 1 and also xk. So what's left is only minus x bar k. So we have x bar k here. This is the same as the left-hand side of the second inclusion here. And then because of the iterate from the CP framework, we know 0 belongs to this set. Right, so 0 belongs to this set. If you scale it by a scalar tau2, 0 is still in the set. Right, so we check both 1 and 2. Now we need to check the inequality. First, we know that xk plus 1 and x2k plus 1 in the IPP framework, they are the same. So this term goes away. And also, epsilon k plus 1 is 0. So we just need to check this inequality. So after ignoring, deleting this term and this term, you just need to check this part is less than or equal to the sum of the two. So that is equivalent to this inequality because here we just use the definition of yk plus 1 in the IPP framework by using this line. So this yk plus 1 minus the yk plus 1 from the CP framework, what's left is this one, tau 2 times k times the difference. So it's just this term here, right? So these two are equivalent. And then here we just divided the whole inequality by tau 2. Okay, this is yk from the IPP framework. This is the yk plus 1 from the CP method. Because here we just use the fact that y tilde k plus 1 in IPP framework is yk plus 1 is in the CP method. But here we just keep this yk as is. This is superscript, this is subscript. Okay, so from here to here is also equivalent. And from here to here, we ignore this term. We are stating a stronger inequality. And this inequality is this is also stronger than this one. So if this holds, then we also have this inequality. So let's check this stronger one. And from here to here, we use the fact that x bar k plus 1 in the method is 2 times xk plus 1 minus xk. So these two are the same. These two differences are the same. So let's check this inequality. Because now the norm terms are the same, so we can ignore them. Just check the scalars. And this is exactly the assumption we assumed here. Right, so with that assumption, going from the bottom to the top, we can show the third inequality. This inequality also holds. So this is going to be the framework. The two inclusions and this inequality is a framework. Because we have, so this is a special case of the framework because here you scale it a little bit by the tau 1 and here you scaled by tau 2. Tau 1 and tau 2 are free except we need to make sure this inequality is satisfied. But with this slightly modified IPP framework, you can still show either the pointwise convergence or the ergodic convergence as would be shown before. And hence you can also get convergence for the CP method. So this is a method for solving the saddle point problem. And this is an instance of the general framework where we do not handle optimization but also saddle point problem. Okay, any questions? Okay, now so this concludes our lecture on IPP framework. Now let's talk about augmented Lagrangian, which is a way to solve the constraint optimization. But we also see how specific methods in augmented Lagrangian can be viewed as an instance of the IPP framework. So we will still obtain the automatic convergence there. Let's begin with an easy algorithm called dual ascent. This can be viewed as the counterpart of gradient descent, because for minimization you want to the most basic algorithm is a gradient descent, but for maximization for the dual problem, because we are maximizing, so you are using the dual information to go uphill. So this is called dual ascent. But we still begin with a minimization problem. Suppose I want to minimize this convex function f of x subject to the linear constraint ax is equal to b. Because we have a constraint, so a natural idea is to construct a Lagrangian.
Is fx convex?
Yeah, we assume convex. Convex, closed convex. So we begin from this minimization, minimizing f of x subject to the linear constraint, and then we construct the Lagrangian by dualizing the constraint. We introduce a Lagrange multiplier y. Y is unconstrained because, so here y is unconstrained because here is an equality constraint. If this is greater than or equal to, usually we choose y to be less than or equal to 0. But here, because this is unconstrained, so we have no constraint on. But this is equality, we have no constraint on y. And hence, we can construct the do function. This is by minimizing the Lagrange function over x. This gives us a function on y. This is the do function, so we call it d of y. Here we reformulate the function by taking out the constant. This is a scalar y transpose b. This has nothing to do with x, so we take it out. And if we reformulate this minimization, this infimum, so we have minus sup over x in this structure. And here, if we go back to the definition of a conjugate function, the Fenchel conjugate, this is nothing but what's inside. So ignoring this minus sign, what's inside here is just the Fenchel conjugate of f at this point minus a transpose y. So here we obtain the do function, noting that here this is purely in terms of y, right? We have no x. Okay. And the do problem, so this is a primal problem. The do problem is to maximize over y for the do function. And usually we have a weak duality. So suppose the function here is called p of x. This p of x is less than or equal to, it's greater than or equal to d of y. And if strong duality holds, we have equality. And here, for maximizing the do function, so just to mimic what we do for minimization in the gradient descent method, here we take a gradient or subgradient of the function, and then we just go uphill. So we just choose the gradient direction. This alpha k is something greater than 0. Right. In gradient descent method, here we have a minus sign. That's because we are minimizing. But here we are maximizing. So we just go uphill. This is do ascent. And this d of the subgradient for d at the point yk is computed from here. Right. So we just compute the subgradient for this one. Take the gradient. Right. Take the derivative. So we have this b here minus b over there. And this part, because you have an A transpose here, so when you take gradient, you need to take the A out and just take the transpose of this one again. So transpose of transpose is just A itself. And this minus sign cancels with this minus sign. So we have A times the subdifferential of F star Fenchel conjugate minus A transpose at the point yk. And because we are taking so here we are taking a gradient or subgradient of the Fenchel conjugate. So this is equal to the maximizer. That's the maximizer of this one. And the maximizer of this one is this xk. Xk is an argmin from this minimization, right? This maximization is equivalent. The maximizer of this one is the same as the minimizer of this problem. And this is exactly, this function here, exactly the Lagrange function when you take y to be yk. Right? This is how we dualize a primal problem into a do one and how we solve it using the basic algorithm do ascent.
Would you please explain last two lines one more time?
Yeah, these two?
Yeah, exactly.
You understand this line, right?
Yes.
Because we stated some lemma before, right? The subgradient for the Fenchel conjugate is the same as the maximizer you obtain here, right? That's a lemma we stated before. So we have this A times xk here.
Yes.
And this xk, as we said, is a maximizer of this one. Maximizer of this one is the same as the minimizer of this one, right? So we are just stating the xk again there. It's the minimizer of this one.
Perfect. Thank you very much.
Okay, so this is the do ascent algorithm. That's one option. This is the most basic option to solve the do problem. We can also make the problem more robust by penalizing the constraint, this linear constraint ax equal to b. So here we penalize the constraint. So you have the constraint both in the as it is in the constraint and also in the object function. If the rho is greater than or equal to 0, then the minimizer of this one, the x will obtain from this minimization, is the same as the x we obtain from here, right? They are the same. So this is an equivalent form for the same minimization problem there. And so we apply the same idea by dualizing the constraint. So the Lagrangian we obtain is this one. Right, this function is called the augmented Lagrangian. So we not only dualize the constraint, but also penalize the constraint. Okay, so if you do the same calculation again, you can formulate the do problem. So in the primal problem, when we minimize some function, one effective way that is more efficient than the gradient descent is using proximal point method, right? As we just talked about many instances of it. We have many inexact proximal point method. So for this do problem, let's also consider applying the proximal point method onto it. So let's consider the proximal point method. Noting that this d of y is obtained from, it's the same d of y here. It's obtained by just the dualizing constraint, but we have no penalty on the constraint. So it's the same d. We want to solve this problem, but do not use the dual ascent, where we use a proximal point method to solve this problem. Right, so this d is the same as that d. This d is not obtained from dualizing this problem. Not to minimize this augmented Lagrangian over x, but just to minimize the normal Lagrangian over x. The d is the same as the d over there. So in the minimization, when we apply proximal point method, we add a quadratic function to make it strongly convex. But here we just subtract a strongly convex function to make the object function here to be strongly concave. So this is just 1 over rho strongly concave. But if you want, you can still formulate it as a minimization problem by just take a minus sign here, right? This becomes a strongly convex function for minimization. And also the d of y is always concave. This is because one of the reasons is that so this is linear in y, and so this is because this is f star. It's a vector conjugate. Vector conjugate is always convex, and if you take minus sign, this is concave. you can also see from here. So this Lagrangian function is linear in y, and you are just minimizing over. You are just minimizing over x. So this is like you have a bunch of linear functions, and you are just for any fixed point of y. I'm taking the minimum among all these functions, right? I'm taking these points as my function value. So to take it in the end is this pointwise maximum for linear functions, and pointwise maximum for linear functions is a concave function, right? As what we shown before, that you have seen. So if you take pointwise maximization, then you obtain a convex function. That is the idea in factorial conjugate. But here it's just the opposite. This is a minimization. So this is a concave function. So d of y is a concave function, no matter the condition on f, whether it's convex or concave. So here d of y is always concave, and this is strongly concave. So in the end, the sum is strongly concave, and this is strongly convex. Okay, so from here we can obtain the augmented condition. So we have 0, because d here is usually non-differentiable. So we have inclusion, not equality. 0 belongs to, let's consider this minimization. 0 belongs to minus d prime of yk plus 1 Right, so this is just the augmented condition of the minimization problem. And here we just reformulate it by using the d prime notation. D prime always takes this formulation. Right, so d prime at yk plus 1 is a times xk plus 1 plus b. So here we have xk plus 1. But here xk plus 1 is not something we have already, because this is an implicit scheme, different from dual ascent, right? Because proximal point method is implicit, and dual ascent or gradient descent, they are explicit. So here you have xk plus 1, but here we have xk. This d prime is equal to a times xk, but here we have d prime equal to a times xk plus 1. This is something we do not have yet. So we need to do some more calculation to obtain that one. the xk plus 1 also has this form. It's argument of the Lagrangian. It's argument of the Lagrangian function at the point yk plus 1. So here we just write it down explicitly. We have yk plus 1 here. And this equivalent, we just ignore the constant yk plus 1 transpose b. And from this line to here, we use the form for yk plus 1. We use this formula. Yk plus 1 is yk plus rho times the primal invisibility gap. Right, so this is yk plus 1. And also, let's consider, because here we have x plus 1, we also have x plus 1 here, so it's not easy to see what x plus 1 should be. So, but because this is arcmean, this is minimization, we can always take the gradient. We can always check the automatic condition. The gradient for this function with respect to x is equal to this one here. Here it's easy, right? This is just a subdifferential. But for here, we take the gradient with respect to this x. This xk plus 1 is fixed, it's just some constant. We take gradient with respect to this x, so there's another A transpose outside. And what's inside is just this part. Okay? And here's a little bit more tricky. You need to observe this automatic condition is not only the one for this minimization, but also it's the automatic condition for this minimization problem. You can do the calculation to see. So if you take gradient, we obtain the subdifferential, and you take the gradient here, we obtain A transpose yk, right? If you take gradient for this quadratic function, you have another A transpose outside, and this will be rho times A transpose Ax at the point xk plus 1. So it's exactly this term, rho times A transpose A xk plus 1, and also minus b, right? So this holds for, this is the automatic condition for both minimization problem. And this one is exactly the same as the augmented Lagrangian over there at the point yk. So this calculation shows an interesting fact that if you apply the proximal point method onto the do problem, so in the end, this is equivalent to minimizing the Lagrange multiplier, right? The augmented Lagrange, minimizing the augmented Lagrangian. Well, if you do the explicit form, if you apply do ascent onto the do problem, this is equivalent to minimizing the Lagrangian. But if you apply the implicit one, the proximal point method, if you do this calculation, it's equivalent to minimizing the augmented Lagrangian. That's the difference. Because here you do not have the rho, do not have the proximal subsides, but here you have the rho. So this rho is both the penalty parameter for the primal and also the subsides for the do. So there is a nice connection between the primal and the do. Right. So when you solve the proximal point method, what you need to do is to first solve the x. Right. This is the first step. So given yk, given the yk, the do function, the do variable, the Lagrange multiplier, you need to formulate this Lagrangian, augmented Lagrangian, and solve for the x in the next iteration, xk plus 1. With xk plus 1, you can also do this iteration, right? Because now you have xk plus 1, you can obtain the update for the do, for the yk plus 1. And then this finished one iteration. So we move on to the next one. So the algorithm looks like this. This is the augmented Lagrangian method, ALM, or we call it method of multipliers, MOM. So first you find xk plus 1. So this algorithm is performing primal and then do updates. The update for x is primal, and then you do the do updates. The do updates is also intuitive because this step is again solving the Lagrangian, augmented Lagrangian, right? Because augmented Lagrangian is similar to what we do here. If you apply let's write down the augmented Lagrangian. I'll row xa plus 1 y. This is the augmented Lagrangian at a point xa plus 1. So the gradient of this one with respect to y. Right, it's just this term here, xk plus 1 minus b. And here, what this step is doing is we take a do ascent step with step size alpha k to be exactly this row. Right, because this is the subgradient is the same for any y, so it's also the subgradient for yk, right? So here we just take a do ascent step. But this algorithm is still not very practical because we still need to so here we still need to solve this subproblem. We do not specify how to solve this subproblem, and it will be even more challenging when the function is more complicated. Suppose you want to minimize this function. You can reformulate it as minimizing f1 of x plus f2 of z subject to ax is equal to z. If you want to minimize this function, you will have f1 of x plus f2 of z. Then your primal variable will be both x and z. It's even more challenging, right? Because you have two variables to minimize. So then we need to have a specific algorithm to solve the subproblem.
Can we take the dual and solve the dual problem and go there?
We still. So let me formulate the problem to you very quickly. But the problem is again, you still have this update, right? You have the primal update and then the do update. The do update is always easy as long as you have the primal one. But now the problem becomes more complicated because you have this composite structure f1 and f2. So in the primal problem, you have what will be replaced at fx will be f1 of x plus f2 of z, right? Then you do not have a prox mapping for the sum of the two. That's more challenging. It's even more challenging than this one. Here, if you assume you have a prox mapping for f, that's doable. But for the composite structure, it's more complicated.
So for that composite problem, would that generate two sequences of iterates then? Would you have an xk and a zk?
Yes, yeah, that's the idea. So we just do alternating minimization. So this comes to the algorithm ADMM. So the problem we want to solve is this one. We want to minimize something like f1 of x plus f2 of kx. ADMM is a quite powerful algorithm, and the full name is alternating direction method of multipliers. As the name suggests, it's an idea of it's a combination of two ideas, right? We do the alternating direction method for minimizing the primal, and we also use the idea of augmented Lagrangian to keep updating both prime and dual iterates. So let's formulate the augmented Lagrangian for this problem. Okay, so the algorithm is pretty much like what we had before the augmented Lagrangian method. So we first formulate the augmented Lagrangian by both penalizing and dualizing the constraint ax equals to z. This is also ax minus z equals to 0, right? And then we associate it with a two variable y, so same as before, y is unconstrained. And then we do the primal update, so these two are primal, and this is a do update. Do update is as before. Once you have the primal iterates, you can formulate the do. But the primal will be obtained by alternating, by doing this alternating minimization. So we first, it's given yk, the do one, and the zk. Then for x portion, we just do the minimization of this augmented Lagrangian over x, and then with the latest xk plus 1, we replace the x by the xk plus 1, and then solve this minimization with respect to z. So this is algorithm. We do the primal in 2 blocks and then do the do update. The nice thing of the ADMM is that it can also be built as an instance of the IPP framework. Once we show it's an instance, then we obtain the convergence automatically. So the ADMM can be shown. So these three updates are the ADMM updates. This is the automatic condition for the X1 X update. This is automatic condition for the Z update. And this is just a reformulation of the do update. And here because in the IPP framework, given this tuple X, Z, so given XK, ZK, YK, we need to find the two other tuples, right? XK plus 1, ZK plus 1, YK plus 1. We also need to find the one with tilde. Right? This is what we usually do in IPP framework. And so we call this tuple as SK plus 1, as tilde K plus 1. And the way we obtain, so these three updates are the ones from the ADMM method. Well, we need to specify what the tilde updates should be, right? But for X and Z, the tildes are the same as the normal ones. The only difference happens to the Y. YK plus 1 tilde is YK plus rho times AXK plus 1 minus ZK. Noting that this is different from YK plus 1 only for the Z update. For YK plus 1, this is ZK plus 1. But for Y tilde, we use ZK. That's the only difference. But this is from the ADMM update. This is the only update difference, but X and Z, they are the same as the tildes, the same as the ones from the algorithm. So this is a way to reformulate ADMM, the three updates, X, Z, and Y. And it can be shown this is equivalent to this inclusion. This is the inclusion that we usually have in the IPP framework, right? We need to define some maximum monotone operator, T, and we need to show some difference of gradient divided by the subsize lambda k plus 1 belongs to this epsilon k plus 1 enlarged operator, right? And this is at the point, some tilde point. Usually in minimization, when it's simple, we just have one block. We just have xk plus 1 tilde. But here, this is something complicated. It includes the information for both primal and do. And for primal, we have two blocks now. So this is something that it has three blocks, x, z, and y. But this is still the tilde point. So this is the same form as what we had before for the IPP framework, but it's just more complicated. And here, what's different is that previously here we just have something like xk minus xk plus 1. But here we just replace it by sk. But we still have another layer of complication. That's the gradient of w. The reason is that here we change the metric. We use Bregman divergence. That's why we have some gradient of w. Well, in the normal case, when you just use L2 distance, when you just use Euclidean setting, so the gradient of the norm square is ignoring so if you have 1/2, then the constant will also cancel. The gradient of 1/2 L2 norm square is the same as the point itself, right? So then the method, this gradient reduces to what we usually have. But here, we just generalize it a little bit by using a Bregman divergence. W here is the distance generating function we have in Bregman divergence, right? Recall what we covered in the mirror descent method. So here we specifically choose lambda k plus 1 to be 1, epsilon k plus 1 to be 0. This is the same setting as in the Chambolle-Pock method, right? And so here this w, this distance generating function is defined as follows. It's a function of x, z, and y, but x doesn't play a role here. So it's rho or 2 times norm. This is L2 norm of z square, and this is L2 norm of y. And also the t is also complicated. This t is actually similar to the t what we have in the Chambolle-Pock method. It's just we didn't specify what t is there. But you can see here. You can see t has two blocks. This part with this subdifferential. So this part basically handles this block, the gradient here, and this is exactly equal to negative this one, so it's equal to W xk plus 1 minus gradient W of xk divided by lambda k plus 1, which is 1. This is just 1. Right, so you can do the calculation to see this part is exactly this gradient difference. And the other part, the subdifferential part, it also includes this part. The whole thing is the gradient difference. Also this one. And what's left is here. This is just the gradient, the subdifferential there, right? Here is the subdifferential part. Use another color. So this is the subdifferential, and it covers this part. And the other one is the gradient difference, which is here. So this is just some algebra. Using the definition of W and also the definition of the mapping T, you will check ADMM is actually equivalent to this inclusion. So what's left is to check the inequality. But I think we don't have time to cover that. Let's talk about the inequality we need to check in IPP framework next time. And then you will see ADMM is another instance of IPP, and hence you automatically have the convergence guarantee. Any questions?只是有了两个 minimize 是两部分。
对，但是。
对。B 只是个 constant， 可以当成零。这是个 constant，B 可以当成零，可以当成对，等于点 D 等于等 D 就是 constant， 跟 G 比的。在上这个问题，肯定有这两个就是都会有定义。不是，这是一个新的问题。这个是 AI。
你的意思是 F 方程很复杂，然后 G 反块和两个。
就差不多。
这个 test specific。
有一些 paper， 但书里特别多。真的很多 first argument 都可以用它来表示。这个是两个在巴西的人最开始从今年的时候，还2000年的上面。我不知道可以删几个 paper 给你。Easy money.
Pollution's bad unless you can make it
Yes.
Franklin Roosevelt. Great Depression. Pettiness fell.